All right, I want to look at this definition box for mutually exclusive. I'm going to give you a definition here for this guy. Go ahead and put the date up here at the top, and we'll mark this off as a new section. So the word mutually exclusive happens when we have two events A and B have zero outcomes in common. So I'll say have no outcomes in common. And then this will be, they are called mutually exclusive. These two things need to exist completely separately. There can be nothing that they have in common. And so I'm going to use, this is the first time we're really going to see this probability notation, but I'm going to go ahead and put it on here just so we have it. What this means is the probability of A and B occurring has to be 0. There is no chance that both A and B occur when they are mutually exclusive. And so there's some consequences of this, which we will talk about here in just a second. Let's look at example 8 on the next page. So we're going to open a bag of M&Ms. You're going to pour one piece of candy in your hand, and you're going to look at the color. This is real data from Mars Inc., the people who make the M&Ms, from the Cleveland factory. Apparently, this is something that I've recently learned, the factories all have different, this is a probability model. I mean, that's essentially what it is. We've got all of our outcomes, we've got all the probabilities. Each factory actually has different probability models, which I thought was kind of interesting. So depending on where your bag of M&Ms came from, there's going to be a different kind of collection of colors that you may see in your thing. Okay, so what I want you to do is, first things first, let's look at this. And I did tell you that this was a probability model. But the question is why? Why is this a true probability model? And anytime you're asked to do that, you're really looking for two things. The first thing is that all probabilities should be between 0 and 1. That would make it a true probability. Anything below 0 or anything above 1 is not a true probability. And we need all the probabilities to add up to 1. So what this is basically saying is we have a sample space. There are no other colors of M&Ms besides the 6 that are listed here. So all of their probabilities should be 100%. There is a 100% guarantee. Now, I don't guarantee a lot of things in statistics. I'm a pretty skeptical person, okay? And we'll see that kind of as the year goes on. It's really hard to be 100% confident in anything. But I am 100% confident today that if you reach in this bag of M&Ms and you have one candy, it's going to be either a blue or an orange or a green or a yellow or a red or a brown. There are no other possibilities for what color M&M that could be. So all the probabilities added up together should be a 100% guarantee. And we should check that. So I would want to add up all of these and go ahead and try this. Pause the video, add all those up. Make sure that we get 1 when we add up all of the probabilities. And you should. And that's what I got when I added all of them up. They are all between 0 and 1. Check, check. I checked both of those, and those are both true. Okay? So the first thing I need to do is find the probability that I don't get a blue M&M. I see this word don't. That to me is kind of dinging off some bells in my head that I could be thinking about a complement or the not blue, the opposite of blue. If I define some event B to be that I get a blue M&M, what question part B is asking me for is the probability of blue complement, the complement of blue. So let's go ahead, I'm going to calculate that down here. We do have a formula for this, and that is 1 minus the probability of blue. Could you add up all of these other probabilities here? Sure. I don't want to do that. That's more numbers, more chance for error. So what I'm going to do instead is take 1 minus the probability that I have a blue M&M, which we are told is 0.207. And if I calculated that, you should get 0.793. This number should be equal to orange plus green plus yellow plus red plus brown, because those would be the options where it's not blue. So if you want to check that, you are welcome to check that. They should be the same. All right, part C, I'm looking for the probability that I get a blue or an orange. So now I'm going to define a new event O. And O is that I get an orange M&M. And I want to find the probability that I get a blue or I get an orange. And I'm just going to actually write the word or, just like we wrote the word and up on this last page 8. The probability that I get a blue or an orange. Well, blue and orange are mutually exclusive. It is not possible to have a blue and an orange M&M in your hand. Remember, we're taking one candy. So that's 0. There is no case in which I can have a blue or an orange. If this is the case, you can take the probability of blue plus, whoops, I don't know why I put Q, plus the probability of orange, the orange M&M O. So let's go ahead and add those together. 0.207 plus 0.205. That gives me O. That's weird. I have the wrong thing on my paper. Okay, so let's add these together. So this would be the probability that I get an orange M&M. Or a blue, I'm sorry. So this probability, we've added the two of them together. This is the probability that we get a blue or an orange M&M in our hand. Again, we're pouring out one candy. So what I'm going to add up here to my mutually exclusive, if you have things that are mutually exclusive, you can take the probability of A or B, and that would be equal to the probabilities of them separately. Okay, just another formula. Actually, you might want to go ahead and star this formula, and remember that this only works for mutually exclusive. If they're not mutually exclusive, this formula will not hold true. Okay, next thing we're going to talk about is two-way tables, and I will save that for the next video.